Interface design requires some good old-fashioned electrical engineering, and that's true of both the digital and analog circuits. Let's review some of the basic concepts in signals and in circuits.
A signal is a representation of the physical state of something, electrical circuit, some machine, over a function of time. We often think about two types of signals. DC means unchanging, and AC generally means changing. We borrowed these terms from electric power. DC stands for originally direct current, whereas AC originally stood for alternating current, but we use them in this more general form. Signals can take all sorts of different varieties. For instance, this is a sinusoid signal. We can represent this signal as a sinusoid is a function of frequency, phase, and amplitude. By varying those three parameters, we can get many different types of sinusoidal signals. We can also deal with exponential signals. Here we have a time constant and an amplitude. Once again, by changing these parameters, we can get a wide variety of different exponential signals. This shows a time domain version of a signal. This signal looks complex, but when we look at it in the frequency domain, we can see that it's in fact composed from two different sinusoids, omega 1 and omega 2. The axis represents frequency, and this frequency domain plot shows that our signal has two components. So we can represent signals either in the time domain or in the frequency domain. Neither one is fundamentally better than the other. Each has its own advantages for different situations. This frequency domain plot shows a signal which has high values at low frequencies and then slowly drops off. We can measure frequency either in terms of radians per second, which we typically write as omega, or as hertz, which we typically write as the variable f. 1 hertz is equal to 2 pi radians per second. The decibel is a unit of power, and it's a logarithmic scale. We often use decibels to describe signals because it allows us to talk about a wide range of values with relatively small numbers. The half power point occurs at 3 dB below the peak. We often use the half power point or the minus 3 dB point as a reference between signals that are passed very well and signals that are passed poorly. A resistor allows a current to flow and produces a voltage in response to that current. Resistance R is the relationship between voltage and current. The reciprocal of resistance is conductance, which we generally refer to as G. And we know that the voltage across the resistor is equal to the current times the resistance. Another way to write this is that R is equal to V over I.
Several physical and mathematical laws guide our design of circuits.
Here's a simple, perhaps unusual example of a circuit that we can use to illustrate some important laws. Kirchhoff's voltage law says that around any loop in the circuit, the sum of all the voltages is equal to 0. This depends, of course, upon us properly defining the polarities of the voltages. But with properly defined voltages, for example, the sum of the 3 voltages across the 3 resistors in this circuit is equal to 0. Complementary law is Kirchhoff's current law, which says that the sum of all of the currents into a given node is equal to 0. Once again, we have to define the directions, but we have 3 nodes in this circuit, 1, 2, 3. The currents that go into each of those nodes sum up to 0. Kirchhoff's voltage and current laws follow from conservation of matter and energy. We can simplify circuits using Thevenin equivalent. So here is a circuit that has 3 different resistors in it. Given a current, it may produce some voltage across its terminals, or given a voltage, it may draw some current. Thevenin's theorem says that we can represent any such circuit as a combination of a voltage source and a resistance. The complementary form is Norton equivalence, which says that we can take any circuit and represent it as a resistance in parallel with a current source. A capacitor also relates current to voltages, but in a different way. In order to represent the behavior of the capacitance, we need to use derivatives. The current through the capacitor is proportional to the change in voltage over unit time. So C dV dt is equal to the current. This implies that we cannot have an infinite current, because that would require an unbounded change in the voltage across the capacitor in an infinitesimally small amount of time. Similarly, an inductor's behavior depends upon derivatives, but in the complementary form. So the voltage across an inductor is proportional to the change in current per unit time. So we can't change the current through the inductor instantaneously.
Linear time-invariant circuits have important properties that guide our analysis and design of circuits.
We refer to capacitance and inductance as reactances. And so we can represent capacitive reactance as dependent upon the frequency of the signal. So capacitive reactance is equal to 1 over omega c, or 1 over 2 pi fc. Inductive reactance is equal to omega times L, or 2 pi f times L. An important set of properties for circuits is linear time invariance. Linearity means that the component behavior is a line through the origin. The fact that the line goes through the origin is very important. A line that intersected the vertical axis at some other point would not give us the properties that we need. Resistance, capacitance, and inductance all satisfy linearity, at least in their ideal forms. The slope of this curve gives us, in this case, the resistance. Time invariance means that the component values do not change. So, for example, we don't start off with the resistance at this slope and then a minute later see the resistance change to a different slope. The combination of linearity and time invariance holds for ideal RLC circuits, and it allows us to analyze them in very powerful ways. The Laplace transform is in fact a general tool that allows us to represent RLC circuits in a very general form. We translate the differential equations into what's known as the S-domain that allows us to simplify analysis. Mathematically, we use an integration in order to transform from the time domain into the S-domain. However, we have standard representations for circuits. However, we have standard representations for RLC, and we can apply the typical laws once we have them in the S-domain. So, for example, the combination in series of 2 impedances in the S-domain is their sum. The combination in parallel of 2 impedances is the inverse of the some of their inverses. The impulse response is the response of a circuit to an infinitely large but infinitely short input. The impulse has a duration of 0 and an unbounded value, so its integral is 1, even though it has no time extent. This is a mathematical convenience, but we can use it to represent the behavior of the signal over time. And once we know the impulse response of a circuit, we can use that impulse response to derive its behavior when we give it other types of inputs. We can classify RLC circuits. Into two different categories depending on the balance between their different component values. In the overdamped case, we see that the response goes up and then asymptotically approaches a final value. In the underdamped case, we see that it oscillates toward convergence to a final value. There is a third critically damped case, which is just at the razor's edge between these two cases. Resistors, capacitors, and inductors are linear, as we said before, but nonlinear devices are critically important because they allow us to distinguish signals and to amplify signals. Diodes, MOSFETs, and bipolar transistors are all examples of nonlinear devices, and we'll see how to use them in many different situations.
To summarize, we can represent signals in the time domain or the frequency domain. Each representation has its advantages in different circumstances. Resistance, capacitance, and inductance are all examples of impedance. Kirchhoff's law and Thevenin equivalence allow us to transform circuit representations to help us better understand what they do. The Laplace transform is an elegant way to describe the behavior of RLC circuits. The impulse response is a fundamental description of the circuit's behavior, and we can use the impulse response to derive its response in other environments.